Hi, I'm going to go ahead and work through the problems that we had on our activity. First, a quick reminder of our basic derivative rules. Whoops, here we go. Let me put these over here on the side. Okay. So remember we had our constant rule, so the derivative of any constant is 0. We have our basic power rule. This is our constant multiple rule, so that means if we're multiplying a function by some constant k, which is different than just a standalone constant. And then we have our sum and difference rules. Okay, so moving over here to this first problem. Okay. I'm asked to find y prime, so I'm looking for the derivative, and y is a function of x. So y prime is going to be equal to, so for this first one, 6.3x, I get 6.3 times x to the, and my current exponent is a 1. And I'm going to subtract 1 from that, so now it becomes x to the 0. And then minus the derivative of any constant is 0. So the other thing is when we come over here, x to the 0, remember anything to the 0 power is a 1. So that's 6.3 times 1. And therefore y prime is equal to 6.3, and then minus 0 is just 6.3. So there's the derivative. Okay. And like I said, once you get the hang of these rules, you'll do this much more quickly. I'm just showing all the steps for right now. Okay, so the second example, really important, whenever you're taking derivatives, a lot of what we do in calculus, we're going to have to rewrite it or use the rules of algebra first. So on this first one, I see these fractions. I'm going to rewrite this as y. So y is equal to, and there's my coefficient. So think of this as being 1/3, and this is in the denominator, so I need to bring it up, x to the negative 3. And then here I've got my coefficient 1/10, so 1/10, and this is x to the 7th power. And now I'll go ahead and use a combination of my rules. Okay, since I'm adding terms together, I can do it term by term. I have my constant multiple rule here, so I've got 1/3 times, now the derivative of x to the negative 3 is going to be a negative 3x to the negative 4th power, because I'm subtracting 1 from the exponent. So negative 3 minus 1 gives me my negative 4. And same thing over here in the second one, I have 1/10 times whatever the derivative of x to the 7th is. So I bring down my exponent, and then I decrease it by 1. So 7 minus 1 gives me 6. And I have to clean this up. So y prime, or dy dx, is equal to, so I got it 1/3 times a negative 3, so that's a negative x to the negative 4th. And then over here, 1/10 times 7, so I get 7/10, and we have x to the 6th power. And you can leave your answer written like this for me. I'm okay with that. Or if you want to, or if you need to, you can rewrite it. This negative exponent could be rewritten. Again, I don't require it, but you can take that as a negative 1 over x to the positive 4th power. And then the 7/10 x to the 6th power, you wouldn't have to do anything to that one. But again, I'm happy with your answer right here. Okay. Let's see, number 3. Okay, here's another one. We got to use algebra first. We don't have any fraction rules. We don't have anything that tells us how to take the derivative, with fractions and fractions involving functions. We will get one later, but for right now, you have to think algebra first. All right, so that's going to be something I'm always going to mention to you guys. Algebra first. Do I need to rewrite this first? So for this particular one, since we're dividing by a monomial, one term, I can divide each term in the numerator by the denominator and then simplify those individually. So y is equal to, so I got 3x to the 5th over x squared, that becomes 3x to the 3rd. On the second one, the x squared cancels, so minus 7. And on the last one, I get 4x to the negative 2. So I've reduced the fractions. I've also rewritten them so I can use my power rule. So now I'm ready to go ahead and find the derivative. So y prime is equal to, so for this first one, again, I get 3 times whatever the derivative of x to the 3rd is, so that becomes 3x squared. And then the derivative of 7, that's a constant, so minus 0. And then on the last one, I have a negative 4 times, and then the derivative of x to the negative 2. So I bring down my exponent, and then I decrease my exponent by 1. So negative 2 minus 1 becomes a negative 3. And now cleaning this up, we have 9x squared minus 0, that goes away, and then a negative 4 times a negative 2, so plus 8x to the negative third power. And there's our derivative. All right, so question number 4, we're asked to find dy dt. That's because y is a function of t. Okay, it's already been rewritten, so we're set to go. So dy dt is equal to, so I've got 3, and then taking the derivative of t to the negative 4, I get negative 4 t to the negative 5th power, because we're subtracting 1, negative 4 minus 1. And then the next term I have negative 5 times, and then the derivative of t to the negative 1. Bring down your exponent, decrease it by 1. Okay, now simplifying my coefficients, I end up with dy dt is equal to negative 12 t to the negative 5th power plus 5t to the negative 2. Again, for me, there's no need to rewrite it. I'm fine with it written this way, but if you needed to rewrite it for something else, the 12 would stay in the numerator because it has a positive exponent of 1, and then the t to the 5th would come down below. And same thing over here, 5 stays, and the t to the negative 2 comes down below. Okay, so for the next one, I've got dx. Remember, this means take the derivative with respect to the variable x. Later on, we'll have functions that have multiple variables in them, and so when we take the derivative, we have to specify which variable we want to take the derivative with respect to. But that's not an issue right now. Okay, so the first thing I ask myself is, do I need to rewrite this? Yes. Again, this is a matter of, got to use algebra first. Put it in a form that allows us to use those 4 basic rules. So I have to take the derivative with respect to x of, this becomes 4x to the negative 4th power. And then the cube root of x, that becomes a rational exponent, fraction exponent, so 5x to the 1/3 power. And now we can take the derivative using our rules. So bringing down the exponent and decreasing it by 1, so we get negative 4x to the negative 5th power. And then for x to the 1/3, I bring down my exponent, and then I decrease it by 1. So I have 1/3 minus 1. Remember, 1 can be written with any denominator, so I'm going to write it as 3 over 3, so I have a common denominator. Okay, so cleaning everything up, I have a negative 16 x to the negative 5th power, and then minus 5/3, 5 times 1/3, and then this is x to the 1/3 minus 1 becomes a negative 2/3 power. And there's our derivative. Same thing, no need to rewrite it for me. All right, number 6. We do not have a product rule. Like right now I have a function of x times a function of x. I can't just take the derivative of these and multiply them together. Okay, we don't have a rule that tells us it's okay to do that, and even though we will get a product rule later, that's not how we do it. It's a little bit more complicated. So for right now, we have to think of another way of simplifying it, and I can just go ahead and distribute to simplify f of x. So f of x is equal to 2x to the 5th power plus 6x to the 8th power. And now I can go ahead and use my derivative rules. So f prime of x is equal to, I'm going to bring down my exponent, so 5 times 2 I get 10, and then decrease it by 1, so 5 minus 1, so x to the 4th. Next term, same thing, I bring down my exponent, so 8 times 6 I have 48, and then decrease my exponent by 1, so 8 minus 1 gives me a new exponent of 7. This is how you will do most of the derivatives for me. You do those steps in your head, so you'll want to show me that middle step where you have to maybe rewrite it algebraically and then take the derivative. Anytime though, if you have, anytime you need to do the extra steps, then you should write them out, especially with, fractions or maybe a complicated expression. But like I said, for something like this here, I do want to encourage you to start doing more steps in your head. All right, that's it.